Hey, so everyone, today we'll be doing section 14.3 on partial derivatives. Maybe we'll get into section 14.4 on tangent planes and tangent plane approximations. Maybe get into 14.5. The partial derivatives, we've already talked about how to get a partial derivative from equation, check. We also did a couple problems where we took the partial derivative from a table. Partial derivative of multivariable functions, like a function of x and y. Well now, how about a three-dimensional graph? So that's why I'm just going to hit the lights here so you can see this graph. We're going to talk about like it fx or fy. Does everyone see there's the positive x-axis? So when we're talking about this, we're going to find the partial of f with respect to x at the point 1, negative 2. And the point 1, negative 2, I mean, that's point A, which is right here. So there's point A. So what we're talking about is like, we're going to think about the rate of change as of the function f as we move in the direction of the positive x-axis. That's what that means. But better than that, isn't it slope? So let's think of that. This what gives, we got to look at what's the slope, right, of the function at that point as you move in the direction of the positive x-axis. So right here, as you move in the direction of the positive x-axis, is the values of f going down or are they going up? We just got to tell whether it's positive or negative. What do you think? You can follow that little ruling right there if it helps. You can put like a line right there just to help you. Would the slope decrease or increase? Decrease. Would you go down? Think of this like you're standing there on a hill. Would you go down or would you go up? If you move in the direction of the positive x-axis, you'd be going down, right? And so the answer to letter A there, we just got to determine the sign of the partial derivative. Letter A, we can say fx negative 1, 2 is negative. Fx 1, negative 2 is, I'll just put a minus sign. Now, what about letter B? We got to find fy at 1, negative 2. We got to find the slope of f in which direction? That would be in the direction of the positive y-axis, which is here. So go to that same point, everyone. Can you imagine if you're on this hill here and you can move in the direction of this positive y-axis, are you going up or down? Going down. The values of f are decreasing, so we're saying that it would be negative as well. Is that what we go with that? I mean, you got it down, it's just, what about this? So you got xx. So that's second derivative. So now you got to think concavity, right? We got to think, what's going on as I move in the direction of the positive x-axis? What's going on with the slope of f? Oh, let me just do that mouse. What's going on with the slope of the function in the direction of the positive x-axis as we move in that direction? Well, that's concavity. So I'll just hit this real quick. This is when a function's concave up, right? Like a cup, and this is concave down. And in which one of these, if these are representing some function in calculus 1 in two-dimensional space, in which one is second derivative always positive? This one, right? And the second derivative is always negative when it's concave down. Remember the definition of this. We're saying that the slope of f always increases along this interval. So concave up, we think of like a cup. Okay? The definition of concave down is, along that interval, the slope of f, the first derivative of f, is always decreasing. I mean, if you want to see an example, look. Let's say the slope right there is what? 3, and the slope right there is 1, and the slope right there is 0, and the slope right there is negative 1. But concave down, we're saying, aren't these slope values always decreasing along that interval? Good. So that's what we're looking at here. You got to look at this. You got to think like this in these images. So let's go to this point again, 1, negative 2. And we're talking about what's the slope of f as we move in the direction of positive x. Not the values of f as before, but the slopes. So we're just looking to see is it concave down or concave up as you move in the direction of positive x-axis. So you'd be going along this little ruling right here, true? As you move in the direction of positive x-axis, we use those rulings to help us see as they're moving that way, because it is a three-dimensional image on a two-dimensional screen, but is that concave down or concave up? concave down, which means second derivative would be what? Negative. So that's letter C, right? So I'm going to write fxx, 1, negative 2 would be negative, which means f is concave down. Does everyone see how I'm using this? I'm thinking like it was concave down there. Now, one more for this problem. How about fyy? So we're like, okay, slopes, what's going on with the slopes? Are they increasing and decreasing as you move in the direction of the positive y-axis? So as you go along that ruling, is that concave up or concave down? Can you see it's like this? It's concave up, isn't it? Does everyone agree it's like a cup? So that would be positive. Cool, is everyone okay with this? Can everyone see that? Sometimes students have a hard time just to go, I don't know where to look. You can use those rulings to help you see if you're moving in the direction of the positive y-axis. You're like, okay, I'm coming this way. There's the positive y-axis. That's why I headed along this one. But can you see it's concave up in the image? And before it was concave down. There you go. And I put an extra practice problem in if you wanted to practice that one as well. Awesome. Hey, I'm going to lower this now. Great job with that. Everyone's okay with that? Awesome. What about partial derivatives? We did equations, we did tables, we just saw a three-dimensional graph. What about contour curves? So let's just, we can do letter A. Letter A says, can you, and all we can do is estimate this value. We don't have an equation, so the best we can do is estimate. Can you estimate fx at the point 2, 1? The first partial derivative of f with respect to x. All right, so let's locate the point. I put a dot on there to help you out. Does everyone see the point right there? So how do we do this? This is just like a table. If I'm going to estimate this, I don't have an equation. And this is basically change in f values over the change in the x values. That's how we can estimate it. And at that point 2, 1, I'm going to use the closest contour values I've got. And those are f values. Pretend these are temperatures in Celsius. It's like, oh, it's 8 degrees Celsius here, it's 10 degrees Celsius here, it's 12 degrees Celsius there. And we're going to find fx at 2, 1. So, let's see, what's the closest contours I can use? Well, at 2, 1, I can use the 10 and the 8, right? Does that work? So I can do 10 minus 8, but you got to tell me what's the corresponding x values. And remember, we're just estimating, so ballpark will work. Give me a ballpark value here. At x equal to, is that x equal to 2 right there? This is a f value of 10. What would be the corresponding x value right there at 8? Will 1.2 work? Okay, so that's what I'm going to do. Change in f. 10 minus 8. I got to stay consistent. What was corresponding with the 10? About a 2. And I said 1.2. Will that work for everyone? Again, I'm estimating. I'm estimating this. It's the best I can do, and I'm looking at this image here. And I'm estimating right there at the 8, because I had to say, what's the direction? Fx. Now, you could have done 8 minus 10, but I did 10 minus 8 over 2 minus this. And what do we get for the estimate? 2 over, what is that, 0.8? All right, what's 2 over 8 tenths? Or what's 2 times 10 eighths? That helps. 20 over 8 or 10 over 4, what's as a decimal? Is that 2.5? Yeah? Okay, so it looks like, everyone, if these were temperatures, what could I say? Think about it. If I moved in this direction, aren't the temperatures increasing? Change in F over change in X. It looks like, you know, it would be like, it looks like it's increasing about 2.5 degrees Celsius per increase of X value on this table here. If those were temperatures. These were just likely made up numbers that I got because I got that image from the textbook. Does that make that? Can you do an Fy in a similar manner? This time I don't need you to estimate Fy, like here, in terms of the value, but could you just tell me would it be positive or negative? That's most important to me. Everyone, we can tell that Fx will be positive because these are increasing, right? As you go in this direction. What about partial derivative of f with respect to y. That right there. So if you move in this direction, to that point, are the values of f increasing or decreasing? Decreasing. So Fy.1, I mean, you could estimate it, but we definitely know that the answer would be negative. I just want to highlight that. Sure, you can make an estimate just like we just did, but do you all agree you will get a negative answer? There you go. Rate of change. Rate of change of f in the direction of the positive y-axis. Cool. Hey, one more with these contours. And we can go back to some equations. Now let's go to this image right here. All we got to do is talk about the signs. All we have to do is talk about the signs. So you're going to fly through letter A and letter B. But then you and I will stop and maybe you'll think about this again to help us understand C and D. Letter A, I just need positive or negative. This is at point P. So there's the positive x-axis. If you move in that direction, are the values of f, these are all the f values. You move in that direction right there, I'll just take a nice horizontal line going through P. Are the values of f increasing or decreasing? Increasing. So fx is positive, isn't it? How about fy? Well, this is at point P. You go through here, the values of f increasing or decreasing? Decreasing. And it's that simple. Not bad, huh? Just rate of change. Well, they're decreasing. Okay, fxx. How do we do this with contours? I want to point out, everyone, when these contours are really tight, that means it's really steep. And if you can think of this as like, pretend that this is representing some terrain. When it's really tight, we're talking about something that's really, really steep. But if the contours are spread apart, all right, that's not so steep. To help you out, it's like this. Let's say see the numbers 2, 4, 6, 8? Say there's a 2 right here and a 4 right here. These are spread out, right? Attach a road between these 2 points. Wouldn't that be a nice ride right there? It's not so steep. But what happens when you have a 2 here and then there's a 4 right next to it, when the contours are really close to each other, like the 6, 8? So 6, 8. Put a road between my 2 hands. That would be extremely what? Steep. So the whole idea is, okay, it's really steep when it's you got the contours tight, close together. It's not so steep when they're spread apart. So when I'm going to go for this fxx, all right, what's going on with the slope of f when I move in the direction of positive x-axis? The slope, okay. So I'm going to go in this direction. Everyone, it looks like, okay, it was not so steep. And then in terms of slope, it was more steep. So it went from not so steep positive to more steep positive. Do you all agree fxx would be positive? And sometimes I got to do that twice. I know it's not so simple. You go, what am I looking at? I'm actually looking at how far apart these contours are on either side of the point P as I move in that direction. So on this side, they were more spread out. On this side, it seemed like they were closer together. So it's like, okay, it was like not so steep positive slope, and then it was a steeper positive slope. That means the slopes did what? Increased. Do you all agree? Now if you're wondering what it would look like three-dimensionally, it's like, it looks like it was like this. It was a positive slope, but it was not so steep. Then it was more steep and positive, so it would be concave up, if that helps. This is what's going on here. It was like, okay, it was not so steep positive, but then it went to something like this, where it was really, really steep. Some people like to think that way. All right, one more. FYY. Remember, look at how far apart these contours are on this side. All right? Do you agree on this side, if you write it P, it looks like these are closer together than on this side? All right, so it looks like really, really close together, really steep. So I'll say large. For steep, can I say large slope? And for not so steep, I'll say small slope. Okay, large slope, smaller slope. But I'm going to add one more word. Look carefully. What was FY before? So be careful with this, especially on a test. So this is what I'm going to say to myself. It went from a large negative slope then to a smaller negative slope. Think mathematically what happened with those numbers. Just make up numbers. What would go from, it went from a large negative slope, and then it changed to, as I went to be in the direction of the positive y-axis, to a smaller negative slope. What happened with those numbers? Okay, I'll make up some numbers. This was like -4 and this was like -2. Did these numbers decrease or increase?
Increase.
Do you notice these increase? So FYY is positive. That sometimes gets students. They go, why is that positive? I'll say it again. Because of the negative values. How FY was negative. So I'm going to think large negative slope, and then it changed to a smaller negative slope, and it's still going to be concave up. So do you want to see where that is? Oh, I use this yellow chalk right here. I'm going to be right here. Large negative slope, and then went to about here, which would have been a not so large, but still negative slope. Smaller negative slope. Everyone okay with that? Hey, great. I always get a lot of questions on this stuff, but it's not so bad. So hey, you got it. I'll turn it off. You got contour curves, three-dimensional graphs, table equations. I have some practice problems. You know, you look in a textbook, you don't get much practice on that problem. So I do want to point out, I'll just grab another one of these. Here it is. I made up this worksheet. And I'll just scroll right down here. And look at that. If you want extra practice, the answers to this worksheet are given to you. Where I knew you might want some questions on this. So look at all the points I made up. I was like, can you find fxx here and fx there and just tell me if it's positive or negative. You know, just tell me if it's positive or negative in terms of the value. So if you need extra practice on it, I know it's not an easy topic to kind of get down, but it seems like you all got it. Thank you. I'll hit the lights now. And before we go into 14.4, because then we've done it all, we've done partial derivatives from tables, 3D graphs, contour curves. We should come back and do a couple more equations. All right, so try this one. Here's a function of x and y. Well, I can put a t. X to the 4th t squared. Cosine we'll put a 2 there. 2y plus t plus 5y. And I need you to find this. Find the second partial derivative. But I have it in another notation. So let's talk about that notation. This is what we're going to find for that function of x and y and a variable t. So this looks weird, doesn't it? See this notation? This is a second partial derivative. But is this fxy or is it fyx? Which one is it? It looks like xy, doesn't it? It looks like fxy. Well, look carefully. You know what this really means? This means take this derivative here, and then take the derivative of this with respect to x. So it means do this first, then this. So believe it or not, this really means this. I'll let you put that in your notes. So if you ever see this notation, you can just say to yourself, okay, I can read the denominator from right to left. This means do the first partial with respect to y, and then take the second partial with respect to x. Do the first partial of the function with respect to y, and then do the second partial with respect to x. Hey, but do you remember Claireau's rule? What is fxy equal to? fyx, remember that? So what if I did it backwards? I'll still get it right, won't I? Cool, because of that rule. So have no stress there. But I do want to point out, this means this. So if this was like a third derivative and it wrote x, y, z, then I would have gone z, y, x. Okay? I know that notation looks funny. Okay, so if it means this, then let's find this first. What is the first partial with respect to y? Well, that's easy. What will that become?
5.
That's 5. Oh, and get this right. Do y'all agree? We're doing partial derivatives with respect to y. So x and the t's are all constants. So they stay, don't we? What's this cosine become?
Negative sign.
Negative sign. Now what about the 2y? We got to apply a chain rule. That's just a constant. So I'm getting negative 2. Everything else stays the same. That becomes sine 2y plus t, and then up with the plus 5. Boom, good job. Was everyone okay with this?
Mm-hmm.
I kept the x constant, I kept the y constant, everything else is held constant except for the y. I differentiate only with respect to y. Now we need fyx. Sometimes this gets people on a test. What's that become?
It stays the same, right? We don't do anything.
Does it? Then what do you
Constant.
mean?
0.
0. Do you agree?
Mm-hmm.
Does everyone agree this will turn into 0? Take the derivative of this whole expression right here with respect to the letter x.
Okay, yeah.
Right? And you're like, well, it's a 5. Oh, hey, how about this? What if this said 5y squared here? I'd still put a 1. 0. It doesn't have an x in it, right? It's a constant. So let's say this said 5t cubed y cubed. 0. So good. Hey, so what happens here? This stays constant. That stays constant. But what happens to this x to the 4th? Because you do have to differentiate that, right? You get negative 8x cubed. And look, just don't change this to cosine. It stays what? Sine the 2y plus the t. Plus 0. And you do not have to put the plus 0. Is that okay with that? Right. That's the only, be careful of that stuff. Be careful of those little things. Like this. Here's another one. Cube x y t. 5x squared. Y minus y cubed plus t. And then when you're going to find g of y at the value 1, 1, 1. So we got to find a partial of g with respect to y and then plug in the numbers 1, 1, 1. Don't let this get you. What is g sub y there? The first partial of g with respect to y. What's this become? 5x squared. Just 5x squared. Brilliant. That's easy. Here's the thing we're talking about. What does that become? What happens to plus t? Yeah, plus 0. Nothing. Right? Take the derivative of that respected. That's what I mean. Sometimes people accidentally let that t hang around. They're like, wait, I thought we keep the t. It's like, you're taking the derivative of that t, which is a constant with respect to the letter y. There you go. Just plug in 1, 1, 1. What's 5 minus 3? 2. Oh, no, the good thing about the equations, we only did a few equations, but this is just going to keep coming up in section 14.4 and 14.5, so we don't have to spend like an half an hour where I like, give you another equation, give you another one. Plus I put a lot of practice problems. If you want practice with like logarithms, you know, doing partial derivatives with logarithms, they're all in there. Cool. I mean, but these are going to come up throughout the problems we work, so we'll get the practice then. We got a lot of practice with partial derivatives from equations. Everyone's okay with that? Excellent. Excellent, excellent. All right. So now, we're going to put down section 14.4. I'll raise this. tangent planes. Haven't we already found an equation of a plane? So now we're talking about planes that are pretty tangent to the three-dimensional curves. Get this.
Graph?
Okay.
No graph.
Oh,
That's all.
no, we're good.
Gotcha.
Or maybe there's like a sphere here, and there's some point. But we can get the equation of a tangent plane to a surface. So remember, a tangent line to a curve, tangent plane to a surface. We just need the equation. Well, it may look familiar. Do you recall this? When I'm going to draw a curve and draw a tangent line. And that's the point, right? You know, Calc 1. Do you know what his equation on a tangent line was? Y minus y sub 1. I'm putting it in point slope form. Equals m times x minus x1. You're going to laugh because the equation of a tangent plane looks just like this. It's going to look like this extended. So isn't that true? In this m, wasn't it the first derivative of x? What's up with that here? It's like, well, you were f prime of x. Okay, y minus y1 equals f prime of x. The equation of a tangent plane is, at some point, and let's use the point, how about x naught, y naught, z naught. That'll be our point. And the equation of a tangent plane will be, it's going to look just like this, z minus z naught equals, okay, I need this. But I need one for the x's and the y's now. Use partial derivative. Fx at the point, x minus x naught, plus fy at the point, the partial derivative with respect to y, y minus y naught. Okay, a lot of times, if you find it easier, I can write this bigger. You might just say, this is really fx. And you might think this is just fy. I didn't want this to bug you, this notation here. I'll get out of the way because then you're always copying. But this just means evaluate at the point. The slope evaluate at the point. Slope of f in the direction of the positive x-axis. That was the slope of f in the direction of the positive y-axis, right? But sometimes, I just want to, this is going to be a numerical value we all find. It's going to be a slope. This right here will also be a numerical value we're going to find. Just like you always did with here. The slope was 3. This might be a 3. That might be negative 2. The slope might be 0. But then it looked just like this. Cool. So let's try one. Heck, I need to give you an equation. How about, I want to use some surface that we're very familiar with. How about the paraboloid? So when I want a paraboloid, it's like a windsock, right? Now let's say the paraboloid is, in fact, I think I'll invert it. The windsock will go like this. Some kind of windsock, let's say 2 minus x squared minus y squared. So that would be some windsock that was like, like this, went up 2 notches on the z-axis, right? And it just opens up like that. Now I gotta pick a point. How about when x is 2 and y is 2? And when I have to pick some point, how about I'm gonna use when x is 2 and y is 2. The only thing is I don't know the z value. What would be the z value there? Because I just made this up. And we'll find the equation of the tangent plane to this surface, which is a paraboloid at this point. How can I get the z value? Just what?
Subtract them.
Yeah, let me substitute. What's 2 minus 4 minus 4? Negative what?
Negative 6.
Negative 6. So when it's almost like, oh, see this when? Here's this. This is 2. Got this paraboloid going on. Like a windsock, right? But we're using a point x equals 2, y equals 2, but then it was down at negative 6. And we're just going to get, what's the equation of the tangent plane right at that point? So the equation of the tangent plane to the surface, let me write the surface down, because I want to make sure when you're copying this, you know what I'm talking about. I got a lot of writing on the board. The surface was z equals 2 minus x squared minus y squared. And the equation of the tangent plane to that surface, at which point? At the point given as 2 to negative 6 is, and I'm just going to write all that out, z minus z naught equals fx, x minus plus fy. And we just plug in all the points. What's that number? Negative 6. What's this number? 2. And what's this number? 2. But these are partial derivatives, aren't they? So now you gotta look at that surface and find the partial derivative of f with respect to x, then plug in the value. Or plug in the values. You'll see one like this is like number 7 on the practice set. All right, well, what's fx? That means what's the, there's f. That's the function of x and y right there. What's the derivative of this with respect to x? 0 minus 2x minus 0? You'll get negative 2x? So this is huge. Do not leave the answer like that with a negative 2x here. I know I'm writing it like this, but we really have to substitute a what? The point. You're getting the slope, it's at some point on that surface. And you do got to plug in the point into the slope. So what's partial of f with respect to x evaluated at the point 2 to negative 6? What's going on here? I'll just write down at x equal to a 2. What do you get?
4, negative 4.
So you will always get a value right there. Always. Don't leave it with like variables and stuff. Negative 4, 12, 6, 2, 0. It won't be negative 2x or something. And how about this guy? What's with respect to y? I can name 2y. Now you got to plug in y equals 2. You get the same number? There you go. You can leave the answer like this. But I'll write it in another way too. By the way, the negative negative becomes a what? Is that what I got right? So see how I got these slopes? Partial derivatives, substitute the value. Or what's another way to write this? Negative 4x plus 8 minus 4y plus 8 minus z minus 6 all equal to a 0. I wanted to show you this is just like the planes we were doing back in chapter 12. Section 12.5 we learned about equations of planes. This looks just like it. Negative 4x minus 4y minus z equals negative 6? Is that right? That'd be 6, no, not negative 6, negative 10. I'm going to double check it. Negative 8 minus 8. All I got to do is plug this back in there, right? Negative 8 minus 8, negative 16. Negative 16 plus a 6, negative 10. Or what's another way to write that? Or I can do what? 4x plus 4y plus z equals what?
Negative 10.
Now positive 10, right? If I
Oh,
multiply
positive,
negative
yeah.
on both sides. These are different ways to write this answer. This was fine too. You absolutely can leave like this. But if it's one of those multiple choice problems, manipulate it to see how they wrote it each way. And why did I do this? What are these numbers here again? The 4 and the 4 and the 1. We don't care about the 10. The 4, 4, and 1. That's the normal vector to the plane. That's that vector what? Come right off that plane right there, right? Now, you said, well, it could have been a negative 4, negative 4, negative 1. That means one's going in what? One direction, going through the paraboloid, and the other one's coming out of the paraboloid. You got it. I mean, you can actually draw them on that picture if you want to. Like, one's going like this, and one's going like that. Right? Positive 1 for z means it's got a slight what? Increase of 1 there. Or decrease of 1 unit. There you go. Okay, let's try another one of these. Can you find the equation of the tangent plane to this surface. Hold up. This way you're like, okay, Professor Master, you've been giving us too many problems where the partial derivatives aren't so hard. So I gotta use ones with e's. Eventually I'll keep working on ones with natural logs and stuff like that so we get practice with it. All right, z equals e to the 4x plus y squared. The point? How about y is 2, but this time x is negative 1. I don't know what to use for z though. Get the 7 away. Get the 7 away. Get this out of the way. That's the equation.
So you have to put those points, right? Plug them in
Yeah.
so that
Anybody know what that z value would have to be?
e to the power negative 4.
What's e to the 0? 1? Good, and you saw I just made this up, so this would have to be a 1. I'm glad, I want you all to look at that and figure it out, because the problems we're about to do after, it's in section 14.4, sometimes they don't give you that z value. So I want you to go, how can I get it? All you gotta do is plug them into the original function, right? Very good, very good. If they don't give you that z naught, you're like, I can go figure it out. All right, let's work this out. It's pretty easy, z minus 1. X plus a 1, right? Y minus 2. What's Fy? And what's Fx? And then we'll plug in the points. So what's the derivative with respect to x? Partial derivative. I used to say partial derivative. The partial with respect to x. 4 times e to all this junk. Nice. 4 e to the 4x plus y squared. Sometimes this throws people off to like, what are you doing? So you gotta think like, how did someone differentiate y equals what? E to the 5x plus 2, and you're like, 5e to the 5x plus 2. You gotta think everything else is constants. And then when you plug in the points, what number do you get? So you evaluate this at the point, negative 1, 2, 1. And 4 times e to the 4x squared, 4x plus y squared becomes 4 times e to a 0, which is 4. Now this has a different partial derivative. What's the partial with respect to y?
2y.
2y e to the 4x plus y squared. So 2 times, oh gosh, is it the same number? Gosh, I don't want you to think these are always the same that happen twice in a row. Sorry about that. And these, sometimes you get 0s and 8s and negative 1s and negative 3s. It can be fractions, but this turns out to be 2 times e to the 0. Right? When you plug in that point, and you get 4 again. And you play? Is that okay with that? And I love it. You all okay with that partial derivative? Nice. Okay, sometimes the most bizarre partial derivatives can sometimes be something like that. No, everyone, we won't find the equation of the tangent plane of that surface. But I was just curious. Does anybody know what fx would be? Because you gotta think of it like e to the 5x, where the y is the constant. So you get y times, there you go. Isn't that weird? But she's right, that is correct, very good. And Fy would be similar, what would Fy be? X times e to the xy. So just keep that other thing held constant. Treat the other variable like a 2. Nice. Hey, doing a great job at this. Now, the other topic in 14.4 is tangent plane and linear approximations. So I'm going to put in parentheses, what do you mean by linear approximations? A tangent plane approximation. the good news is you're staring at the formula. Now this is the equation of the formula. Do you remember doing linear approximations in Calculus 1?
Mm-hmm.
This is very similar, except now we're doing what's called, it's still called a linear approximation, which is called a function L of x and y, but we use the same formula. So linear approximation will be the same formula here. I just got to solve for z. That's all. So if I solve for z, what would I get? That would be my equation for the linear approximation. What would z?
Plus z naught.
Z naught plus the
Rest of it.
fx value evaluated at the point. Here, I'll squeeze it in there. Times x minus x naught plus fy evaluated at the point. I'll squeeze it in there. X naught, y naught, y minus y. All right, it's the same equation, right? So all I did was add a z naught to the other side. So please remember linear approximations, also called tangent plane approximations, is the same thing as the equation of a tangent plane, except you're just solving for z. And you know how they like to write this? You probably remember in Calc 1 they wrote this as L of x for linear approximation. Well, now it's a function of two variables, so we write it as L of x and y. L of x and y. And again, if it helps, sometimes I don't write all that jargon there. I'll just go fx times x minus x naught plus fy times y minus y. Maybe that looks a little bit prettier. I didn't write the little x naught, y naught thing in there, because you know that you're always going to evaluate the slope at the points. So I'll give you a problem. But good news is, like, I don't have to memorize a whole new formula or equation. It's the same thing. Okay. All right, try this one. For h of x equal to, how about sine of 3x plus cosine of 2x plus e to the 2x plus y. At the point, so this is interesting. They only gave you the x and y. Here's what I was talking about. But for this function, can you find the linear approximation? Find the linear approximation. To h of x. And all this is, if you're curious, this is just there's some, you can think of a three-dimensional surface. You're able to make estimates right off that surface at different points. So can you find the linear approximation to h of x at that point? 0, 0. All right. So I'll write this out. L of x comma y, aka z, equals, I gotta put something there. And when I'll pretty this up, I just want to start there. What did I forget? I didn't want to forget this other
Z naught.
The z naught. That when you do this, that there's a z naught here, z naught added to that, right? I'm gonna put that here. The second thing is you might say, well, this wasn't an f, it was an h. So I can use h, x, and h, y. But this is looking good, right? And I just gotta add this to this. That's all. This would be the linear approximation to h of x at 0, 0. But what the heck is z naught? This is what I was talking about. They did not give you that number. Last few problems I gave it to you.
Me too.
And how'd you get that?
Just plug in 0 to x and y and see what it
Outstanding. He just took these two numbers, that's x naught, and that's y naught. He plugged it into the original function of h, the original function to find the corresponding z naught value, which would be just h of those two values. So when you agree it's a 2? He said sine of 0 is 0, plus cosine of 0 is a 1, plus e to the 0 plus 0 is another 1, and he's getting a 2. But he's getting this number. I must be clear, because you might look back to your notes and go, where did the 2 come from? Because it wasn't given. He just plugged these two numbers throughout the original h of x. Just wasn't given, you have to figure it out. Cool, so you won't let that bug in, it does. Alright, this is a partial derivative. What's partial respect to x? Oh, and this was a y, I apologize. That one right there? Right? Let me look. Is it? Oh my gosh. My apology. Keep it an x. I thought they changed another. This is the only place where you have the y. So when we're doing our partial derivatives, we'll just be really careful. At least I know what this is. X minus the 0. This is y minus the 0. But what's this partial derivative? What's that partial derivative? What's the partial respect to x? I get 3
Cosine 3x.
cosine 3x.
Minus 2 sine 2.
Ooh, minus 2 sine 2x. Chain rule. What's with that respect to x?
2
2
e
Plus 2 e to the 2x plus 1. And then, remember, this doesn't all get jammed there. You will always put a number here, numerical. Numerical slope. That's what it represents, the slope and direction of the positive x-axis of this surface. That's 3 minus 0 plus 2. 5. So all that evaluated at that point. All this. I can just put a yellow over. All this at the point 0, 0. This derivative should be easier. What's this? Partial respect to y? Just deal with that.
Just e to the 2x.
Just e to the 2x plus y. Right? Because you derive e to the x, e to the x, and 2x is just a constant, you gotta, so it'll be e to the 0 plus y, you know, oh, excuse me, we rewrite this and then you multiply this by 1 here. And you gotta plug in a 0, is that just 1? Done, there you go. Okay, I'll let you copy this.
Was it intentionally written as h of x, not like h of x and y? Like,
Oh, it should say h of x and y, and I think there's a typo on that. You just brought up a really good point. That should be a function of x and y, but I copied it from the change, and now you're realizing a typo off the paper here. Or my eyes didn't see the y. That's really what happened. I was trying to do one like number 9 on the practice set. If anybody's curious, but it did have a function of x and y.
That was this one.
Yeah. Yeah, this one right here was like number 9 on the practice set. And they had this right here did have a comma y. It was a function of x and y, and that should be there. Man, Matt, thank you again. I appreciate that. Was that okay with this? That's the linear approximation. That's the tangent plane approximation. What do they have you do with this? Sometimes they'll say now use your linear estimation. This would be like an extension. To estimate let's see, when they ask this, I'm going to make up some numbers. These will be numbers really, really close to 0, 0. But use your linear estimation, or approximation. That's a more appropriate word. Use your linear approximation to estimate L of, okay, 0, 0. How about 0.1 and negative 0.1? We don't have to do it, but what would you do? What would you do with these two numbers? Just substitute it into the what? Yep, you don't have to do it now, I just want to make sure you know what to do. That's the idea. Now you can use this and you can estimate values that are really close to it. But when they ask this, you'll notice they always give values very close to it because, everyone think of a surface and you got a tangent plane at this point. Well, what happens to the tangent plane as you get further and further from this point? The tangent plane keeps what? extending further and further away, right?
Mhm.
That's the idea. So when they ask that, it'll be something really close to it. Sort of like you did in Calc 1. They'd be like, use it to estimate and they give you a value right close to where you were getting at. The point that was used. If they used x equal to 2 in Calc 1, okay, estimated about like 1.9. Excellent. Hey, we're gonna do the same thing. But this time, it's like right now, we just talked about linear approximations, tangent plane approximations. And you have to be honest, you sit there and you're kind of like, what the heck is that helpful? What is that? Where is that gonna help us? So we're gonna do a problem like that. It has a table. I can pop open the screen here real quick. You can see the table. And I'll pass it out to you. So we're going to do a linear approximation problem. Well, one that has, its application. We're going to do one like number 5 in this sheet. So, these are some practice problems that I added. I'll pass them out. Can you pass one back? Thank you. We're going to do number 5 together from this sheet. And the only reason I wanted to pop it up here is so you can see the table. Again, I want to save the amount of time that you'd have to sit here in class and copy